Good morning, everyone. Let's get started. So today I will talk about AI-enabled UAS detection and negation. I'm very honored to be invited to give this speech at this wonderful event. So I'm Hoping Song, an assistant professor of electrical engineering and computer science at Amarillo Aeronautical University. Also, I'm the director of security and optimization for Network Group Lab, Soon Lab. So today, in my presentation, I will talk about 3 parts. The first part is introduction. I will talk about myself, my team, and our Counter UAS research. Then, the second part, I will talk about the detection and negation for protecting against the small UAS. This is the main body of my presentation. So, I will talk about the Counter UAS problem. Then I will present my solution. 2 parts, sensing and neutralization. In the end, I will talk about the performance evaluation of our unique solution. In the end, I will give a summary. So the first part about myself. I'm an AI and counter cyber for autonomous unmanned collective control subject matter expert SME selected by the U.S. Special Operations Command. Also, according to the one website called guide2research.com, I'm on the list of the top scientists for computer science and electronics in the world and in the United States. My ranking here. So about my team. My lab is named after my last name. The mission of my lab is to advance research and education through discovery and innovation at the confluence of 4 areas: AI, machine learning, cybersecurity, privacy, communications and networking, and cyber physical systems. My lab is called, the Soon Lab. So here, as denotes security, we conduct research on cyber physical system security and privacy. O denotes optimization. We conduct research on big data analytics, AI, machine learning, signal processing and control. N and G denotes networked group. We conduct research on Internet of Things, cyber physical systems, software-defined networking, airborne networking, such like that. About my team is very big. Now we have 9 PhD students, 2 visiting scholars from Europe, and the NGA Explorer program. Also, I supervise 7 master students. About our Counter UAS research. My lab developed a new technology that detects and safely neutralizes rogue drones without destroying them or causing them to crash. In fact, we started this research in 2017. So we developed this technology last year in 2019. An Amarillo news release generated a large volume of media coverage about our new technology, unique technology. This story generated at least 100 media mentions, reached a total potential audience of 16 million people. So here, for example, the Security Business magazine for security executives, a Florida professor invents AI program to hijack rogue drones. Also, I believe everyone knows, the IEEE Global Specification, Engineering 360, new technology hijacks intrusive drones. Also, the Association for Unmanned Vehicle Systems International, Amarillo professor develops Counter UAS tech that safely grounds unauthorized UAS. Also, U.S. News and World Report, John Zacher, Daytona professor, invents intelligent system. Also, Fox, Amarillo team develops drone hijacking technology to secure critical airspace. New Atlas, AI system grabs the reins of wayward drones. Also, our local news media, Daytona Beach News Journal, John Zacher, EREU professor in Daytona, invents system to seize control of unmanned aircraft. Also, we have a lot of other media mentions. If you are interested in our media coverage, you can refer to these, the web links or search online in Google. So now, let's say, also, our research has attracted attention from a lot of agencies like UN, United Nations, the International Civil Aviation Organization, ICAO. Federal level in U.S., the Federal Aviation Administration, FAA, U.S. Special Operations Command, U.S. Central Command, Defense Threat Reduction Agency, also DHS, U.S. Department of Homeland Security, U.S. Air Force, such like that. So now let's move on to the second part, the detection and negation for protecting against small UAS. Introduction. There are many types of airspace restrictions in the United States. So here is a list of restrictions that commonly affect UAS flights, like the security sensitive airspace restrictions, temporary flight restrictions, restricted or special use airspace, stadiums and sporting events, wildfires, airports. So here, according to Federal Aviation Administration, the reports of UAS sightings from pilots, citizens, and law enforcement have increased dramatically over the past 6 years. So now, FAA receives more than 100 such reports each month. So here, from this drawing, you can see from the 2014 to 2019, 6 years each month, how many UAS sightings report FAA received. So this one, it's about, the UAS sighting reports in each state in the United States. So here, it's interesting. You can find for some tourism hotspots, like, the Florida, we receive, more than average, the UAS sightings reports. Also, like Washington, D.C., New York, also in California, we have, the received more UAS sightings reports. So there is a need for detection and negation for protecting against small UAS. So typically, such system is composed of two subsystems. One is the sensing subsystem. The other is the neutralization subsystem. For the sensing subsystem, the ideal sensor subsystem will detect multiple small UAS at a distance of 1 km or greater, and will support highly automated operations. The neutralization subsystem, the ideal neutralization subsystem will disable or destroy multiple small UAS at a distance of 1 km or greater, while ensuring low collateral damage and low cost per engagement. So here, from the literature review, we found, there are several, different categories of UAS detection approaches. 5 here, acoustic, vision, passive, radio frequency, radar, integral detection, such like that. For acoustic, we can, divide into acoustic spectrum recognition, TDOA localization. Vision, we can divide into object detection and object classification. For the passive RF, 3 subcategories: RF spectrum identification, data traffic pattern analysis, motion RF coupling analysis, radar, active radar or passive radar, integral detection, data fusion. So now let's see our solution. Our solution is the AI machine learning enabled real-time UAS detection and negation framework. The uniqueness lies in the cost effectiveness, and our solution is friendly. So for the sensing subsystem, our system is the machine learning enabled real-time localization. We use wireless acoustic sensor networks to identify the appearance and estimate the presence of approaching UAS. For the neutralization subsystem, our uniqueness is machine learning enabled real-time radio channel identification and negation. We use software-defined radio transceivers to specify and decode the UAS telemetry protocols. Also, we use decoded information to generate control command for guiding UAS to stay away the sensitive areas. So here, this is our proposed physical deployment. So we divided, area into 3 areas. In the middle, it's a sensitive area. We don't want, the UAS to enter this area. Outside, we have the reactive area. When the UAS approach this area, we will take action. The outest circle is a detection area. When the UAS approach, detection area, we should detect, the approaching UAS, after the detection, we will take action to avoid UAS to enter the sensitive area. So here you can see the physical deployment. For the detection area, we will deploy, distributed acoustic sensor nodes. Here also, beacon receiver. The next one, the inner circle, it's a reaction area. We will use a software-defined radio transceiver. Also, we can use surveillance UAS, control center, authentication server, such like that. For the inner circle, it's a sensitive area. So for the data links involved in the UAS detection and neutralization, it's like this. Here, it's a ground control station. We have, the emitter zone, the unsafe and unauthorized, the operations. Here, between the ground control station and, the approaching UAS, there will be control and telemetry and analog video stream, in the between. For the SDR, software-defined radio transceivers, between the ground control station, there will be, the video warning information from the, we will send, video warning information from software-defined radio transceivers to the ground control station. Also, the between the approaching zone and the software-defined, the radio transceiver, there will be simulated control command. We will guide the zone to stay away, the sensitive area. Here, also we have the protocol analysis server. So for our proposed, architecture, UAS detection and neutralization architecture and workflow, it's like this. From top, we have the detection layer. On the bottom, it's the reaction layer. Here, for the detection layer, we will collect surrounding acoustic signals, and then we perform pattern recognition on signal patterns. Then we check whether the zone flight is, authorized using its beacon. Then we estimate the zone's position and invoke the reaction layer. For the detection layer, the related infrastructure include the beacon receiver and wireless acoustic sensor network. For the reaction layer on the bottom, if we detect an unwelcome zone, so we will scan the radio channels and ISM frequency and perform spectrograph analysis. Then we identify its analog video streaming and telemetry control channel. We transmit video warning information. Then we can block its telemetry channel to trigger its returning strategy. Then we can try to identify its telemetry protocol, transmit spoofing control command. If this doesn't work, we will take, consider further actions. So here, for the reaction layer, related infrastructure, including the surveillance zone, SDI transceiver control center, and authentication server. So now let's say the acoustic identification and tracking. Here, the pattern identification is based on acoustic. So here, why we use this? Because, our finding, it's based on the, from our finding, we found, for the natural background, heavy rain and hovering quadcopter and hovering hexacopter, the power spectral density, the graph, it's different, right? Now you can see the for these 4 types of acoustic, the pattern, it's totally different. Workflow for the acoustic pattern identification. So for this part, typically we will use 3 parts. One is the dimension reduction model, and the digital filter parameters and the classification model. Use these 3 parts. When we use these 3 parts from the left to the right, let's say we will pass several steps like smooth filtering, FFT, and dimension reduction, and support vector machine classifier. Then we will get the result. This is our workflow for acoustic pattern identification. So now let's see the workflow for the acoustic localization. So here we use acoustic. So here it's a microphone array. So from microphone array, we can collect signals, acoustic signals. Then we can apply acoustic signal pattern recognition. Here, after that, we collect signals within 1 second and apply to the low-pass filter. Then we perform the autocorrelation on signal with highest amplitude. We derive average the autocorrelation period of signals from each channel. Then we divide the signals from all channels into time domain segments. So after that, we derive the amplitude of signals in each segment and derive the latency between the different channels in each time segment. Then we can invoke central server to estimate the pricing of zone. So radio channel identification and reaction. This is the negation part. With the workflow start from the left. With software-defined radio receiver, we can get the IF quadrature. Then we can do the radio frequency recognition and decoding. Then we can send the video warning frame. So also, here we can, if the video warning doesn't work, we can send, the spoofing command. So here, the both can be sent to, the transmission processor and then the RF transmitters. So here, in fact, after, RF recognition and decoding, we can identify telemetry protocol. Before that, we need a protocol classifier. If necessary, we need to take further actions. So here is the modulation, identification, and the data packet recovery. So here, the proposed modulation, identification, and the data packet recovery set is like this. Also from, the left to right, the software-defined radio receiver, we can get IF quadrature data. Then we do the spectral waterfall graph analysis. Then we can get the bandwidth, operational frequencies, and the active time slots. Then, the quadrature demodulation, we can get the quadrature components. After that, constellation graph analysis, we can get the modulation pattern, identify telemetry data or video channel, generate video warning frames. Also, from the constellation graph analysis, we can do the IQ demodulation and clock recovery oversampled baseband samples. Then symbol timing and date rate. Also, we can generate, the raw data packet. Workflow for the protocol identification. So the workflow is like this. We will use, the UAV talk data packet generator, multi-V data packet generator. The UAV talk and the multi-V are two popular protocols for UAV. Also, the random data generator. So with these three, we can encode and vectorization. Then we can train our classifiers. Then, the protocol decoder with raw data packet and the local geographic coordinates. We can determine data packets can be decoded or not, right? If yes, we can send, the control command. If no, we need to take further actions. So now let's see our performance evaluation result. So here, for the acoustic detection, to evaluate the performance of our acoustic detection, the topology for our training and evaluating the classifier is like this. For the our training set, so we can get the sound of the test zone 25%, sound of heavy rain 25%, sound of natural background 25%, Gaussian random noise 25%. Then, we 100%. We can divide it into three parts. Training set 50%, test set 30%, and the combined signals 20%. So here for the training percent, we can do the vectorization FFT, PCA primary component analysis, and the support vector machine, support vector machine, one versus all. Then we can do the performance evaluation. This is our topology. So here, this is our acoustic detection result. I showed the real result, like the relation of FFT size and the contribution rate of training samples. We use 4 different FFTs. Also, I showed the relation between the number of the component and the performance of classifier. Also, relation of signal to noise ratio and the classification to positive rate, and the relation of SNR signal to noise ratio and classification false positive rates. For the rain, natural background, and Gaussian random noise. So the next one is our acoustic localization. So we showed the autocorrelation result of signals from natural background signal and rain, autocorrelation results of signals from the test zone and the Gaussian noise, interference tolerant threshold in different circumstances for signals latency detection, and overall relative error analysis on acoustic location. So this is our radio channel identification. We tried, the different, protocol like UAV talk, multi-V, random, different, the combinations. So the left one is the dimensions, the probability versus prediction, the x-axis is dimensions. For the right one, it's performance of the classifier with different beta error rates. So the x-axis is beta error rate, y-axis is probability versus prediction. So to summarize, our Counter UAS research, we developed a holistic solution to detection and negation for protecting against the small UAS. So two subsystems. One is the sensing, the other is the neutralization. So now, what we are doing now? So we are working to detect multiple zones simultaneously, and we are working to detect and neutralize multiple zones at a greater distance. Because for the acoustic, typically the distance is not so big. So thank you for your potential interest in collaborating with my lab, Sun Lab, on commercialization of our unique technology. We value your interest in collaborating with us and welcome any opportunities to explore the possibilities of working with you. So references, we published the several journal and conference articles related to our unique technology. The first one is published in Actual Communications magazine in April 2018. The second one is our comprehensive survey of Counter UAS technologies, state-of-the-art challenges and future trends. It will be published by Actual Aerospace and Electronic Systems magazine this year, sometime this year. Also, we have two conference articles. One is in the SANS, Integrated Communication, Navigation and Surveillance Conference. Last year, we received the Best Paper Award from the SANS conference in the Cyber Physical Security track. The other conference article is AIA Actually Digital Avionics Systems Conference, DSC 2020. So that's it. So if you have any question about our research, please feel free to contact me. So this is, sunlab.us is our group's website. Here is my email. Thank you.